Hi there. Welcome to Lecture 17 of Machine Learning from Data. We're going to be addressing the memory and efficiency issues in this technique that we discussed last time called the nearest neighbor. So let's have a quick review of the nearest neighbor technique. It's a very simple, powerful technique. Okay. Now, it's based on similarity, and we discussed the Euclidean similarity. Okay. The Euclidean distance between features of two objects is a measure of similarity or dissimilarity. And, the nearest neighbor technique is a very simple technique. It uses similarity directly to classify a new test point by searching for, the closest, the most similar object in your past, in your database, and then using that object to classify the test point. Okay. And because you're ready to go the moment you have your data, you have no training. Okay, so there's no training involved in the nearest neighbor technique. And we extended the nearest neighbor technique to the k nearest neighbor, where instead of just looking at the one nearest neighbor, you take your k most similar objects to you, and then use those k in a majority vote to decide, what the classification is of the test point. And what we showed last time was that, if you choose the number of nearest neighbors to look at going to infinity, but not too fast, then you can get optimal out-of-sample performance. Now, let me emphasize two things here. The first is it's out-of-sample performance we're talking about, okay? And the second thing is that you get near optimal. So not, the best that, the best machine learner on earth can do. The best that anyone, the target function can do, the optimal performance, okay? Now, there is a problem with the nearest neighbor as is with one nearest neighbor, which is that, the in-sample error is always zero, so you will never know what your out-of-sample error is. But with the k nearest neighbor, with suitably chosen k, not only do you get optimal performance, but your in-sample error converges to the out-of-sample error. And so you will also be able to look at your performance and say whether or not you are succeeding, okay? So here on the left, I'm showing you an example of the one nearest neighbor technique and, what happens when you do the 21 nearest neighbor rule on the digits data. Okay, and what you can see is the one nearest neighbor kind of overfits, and the 21 nearest neighbor sort of, is a much smoother. This jaggedness is occurring when, the decision boundary switches from one of the data points to the other data point being the nearest. Okay, so in some sense, you cannot avoid sort of these, sharp switches in the decision boundary. Okay, and so what we observe here is that k, the number of neighbors you choose to look at, plays the role of a regularization parameter. And, there are several good ways to choose k. The first is using the theory, which says that if you choose k, let's say, proportional to the square root of n, then you will converge to the optimal performance. Okay. The other approach, but now that requires, this optimal performance convergence requires n large, and we don't know how large that n is. So in reality, you have a fixed n. And so a very good approach to selecting, the value of k, just like selecting the value of the regularization parameter, and k plays the role of a regularization parameter. K too small, you overfit. K too large, you underfit. Okay, so you can use validation or cross-validation to choose k. Okay, so those are two very useful ways of deciding what value of k to use. And if you're lazy, it turns out that in practice, k equals 3 works quite well. Okay, so already we have 4 fantastic properties of the nearest neighbor algorithm, and now here comes a 5th one. Okay, when it comes time to justify to your client, why am I classifying this test point in this way? Why is this customer getting credit? Why is that customer being denied for credit? I can just say, well, it's based on this data point in my data, or these few data points in my data. And look, for those few data points which are very similar, what's happening? I'm rejecting or I'm accepting. Okay, so easy to justify the classification. Very easy to do multi-class. You can extend this to multi-class without any effort. Because you look at your nearest neighbor, and depending on the class of the neighbor, you classify your test point. So if you have 10 classes, you can still do the same thing. Look at which class is your nearest neighbor. Okay? Very easy to adapt to regression or logistic regression. For regression, you don't take the majority vote among your k nearest neighbors, you take the average. For logistic regression, when you want a probability, you take the fraction of your k nearest neighbors that are +1. Okay? So look at that, all those beautiful properties. It seems like it makes machine learning trivial. Okay? Well, the problem is, the challenge with the nearest neighbor algorithm is that it is computationally demanding, very computationally demanding. Okay? And that's what we're going to address today. So we have a single focus today, how to address the computational demands of the nearest neighbor. And there are 2 types of computational demands. So the 2 computational challenges are basically memory and efficiency. So memory, why? Because, there's no training. To classify a new test point, you need to compare with all the data. Okay? And so you need to be carrying around as baggage the entire data set. Okay? And efficiency, why? For the same reason. To classify a new test point, you need to you need to find the nearest neighbor. So you need to search among all the data to find the nearest neighbor. And that's a costly task, especially if you have to do it many, many, many times. Okay? So let's take a couple of examples. Supposing that you have 1 million data points and you're in 100 dimensions, so d equals 100. Okay? And let's say we're storing the data in double precision, so you have n data points of each of dimension d, so the memory requirement is order of nd, and that's about a gigabyte. Okay? Now if you're in 1 million dimensions, that's 10 terabytes. So we can't be just roaming around with these kinds of huge data sets, okay, in order to classify a test point. Now where might you find a 1 million dimensional data set? Well, that's very typical. So the dimension of a high resolution image is approximately 1024 by 1024. Let's say that's 1 million. Okay, okay. So memory is an issue. Okay, and okay, these are just small data sets compared to what a 5-year-old is doing. So imagine a 5-year-old. By the time they're 5 years old, they've seen multi millions of images which have been streaming in a few tens or 20 per second. Okay, and you think that the 5-year-old has stored every image they have ever seen so that they can classify the next horse that comes along? Highly doubtful. Okay? So there must be something going on there, and maybe we can emulate that, and that's a path to perhaps solving the memory issue. Okay. What about efficiency? Well, let's take an example. Same example. You have 1 million data points, okay, in 100 dimensions, and let's imagine that you have some normal processor like a 3 gigahertz processor. So in order to find the nearest neighbor, you have to compare with n data points, and usually the similarity measure, if it's a reasonably simple one like the Euclidean distance, to compute the similarity to a data point is an order of d operation. So the running time to compute the function g of x on one test point is order of nd. That's heavy. Okay? And in this scenario with a 3 gigahertz processor, that's about 3 milliseconds to just compute the function once. Okay, but now imagine that you're training and you have a value of k, let's say 10, and you want to compute the cross-validation error. So you have to basically compute the function n times, okay, on your n left out points. Okay, and so that's going to take about an hour. Okay, still doable. Okay, but now what if you have to compute the cross-validation error for a whole bunch of values of k, let's say 1,000, in order to pick the best value of k. So now you're talking about a month of computation, okay? And that's just to pick the value of k for this simple problem. Imagine if we were in 1 million dimensions, that's going to be 10,000 months. We cannot afford that in practice. Okay, so let's look at the two basic approaches to address these two problems. These two problems are going to be our focus for today. It turns out that one of the techniques we will develop in order to address the efficiency issue will also be useful and will give us an introduction to unsupervised learning. Okay, but what are the two basic approaches? Well, to address the memory issue, and this also will address the running time issue, is remove some data, reduce the amount of data. For example, you have 1 million data points, but the odds are many of those are redundant or useless in some sense. Okay, and we'll see exactly what we mean by that. Okay, and basically this means if you compare to the 5-year-old, who's able to classify horses without any error whatsoever, they're not storing every horse in every pose, at every time and in every, lighting scenario that they have ever seen. They're not storing every single one of them. They're probably picking a few representative horses, a few representative dogs, a few representative houses, a few representative balls, and so on. That's what's stored. Okay? And so maybe we can try to emulate that. Okay? And so we will develop at least one algorithm that will, in a principled way, throw out a lot of the data that is more or less useless and keep just the data that you need. Okay? And this is called condensing the data. Okay, so we'll study one technique for condensing the data, which reduces the amount of data. And once you have reduced the amount of data, compute time also will reduce in a proportionate way. Okay, so reducing the amount of data addresses both issues, the memory issue and the efficiency issue. Okay, but then, given that the data set is now fixed, okay, it's possible to develop specialized data structures in which you store the data so that finding the nearest neighbor is more efficient. Okay, and this, by the way, is a very interesting, challenging problem. So how do you store data? What are the correct geometric data structures for storing data so that you can search for and output the nearest neighbor efficiently? That's a research topic, and you can pull up, any theory of computing conference proceedings, and you'll see at least a few papers on how to make this fast, how to make this more efficient, how to make this more accurate, and so on and so forth. So that's an open problem. But we will develop some techniques, some heuristic techniques to address the efficiency issue. So, reducing the data and storing the data in a specialized data structure can help with the efficiency. Okay, so let's talk about reducing the data. In particular, how do we identify irrelevant data? How do we identify irrelevant data? So, here's an example data set with some red X's and some blue circles, and we studied last time how to construct the nearest neighbor classifier. So k equals 1. Okay, basically, you construct perpendicular bisectors, and then each data point owns a region, and that region inherits the color of the data point. Okay, and so this is the region that has been produced by the one nearest neighbor algorithm for this data. So now you're ready to classify a new test point. Now you might ask several interesting questions. Do we need to store all the data in order to remember this classification boundary? And the answer is no, because look, if you look at these 3 blue points down here, which I'm pointing to, and if you look at these 2 red points up there, which I'm pointing to, well, they're kind of redundant. They don't have any, if I move them around, for example, they're not going to change the decision boundary. The decision boundary is in some sense determined for the nearest neighbor algorithm. It's in some sense determined by the data points that are closest to the boundary. Okay, so let's see what happens if I remove those irrelevant data. Okay, look, I removed. So I've sort of shaded them out. I've removed these two red data points and these 3 blue data points, which we conjectured were kind of irrelevant. And now I have this condensed data set of blue and red points. And for these blue and red points that are remaining, the decision boundary is exactly the same. Okay. So we say that this condensed data set is decision boundary consistent. In other words, if you did the one nearest neighbor classifier with the reduced data versus all the data, you'll get the same classification for every possible test point. The decision boundaries are identical. What that means is that the final hypothesis has not changed. Okay? So let's ask a couple of questions just to see if we're all awake, including myself. Okay? Does the in-sample error change? So what is the in-sample error? The in-sample error is you have a hypothesis G of X, which is given by the red and purple regions, and you use this hypothesis to classify all the in-sample data, and what's the in-sample error here? It's 0, because that's what the one nearest neighbor accomplishes. What's the in-sample error here? Now, it's clearly going to be 0 for the data points that are left in the data, because the decision boundary is built from those data points. Okay, but what about the other points? Well, those other points have no effect on the decision boundary from the previous case, since the decision boundary is the same, and that decision boundary got the thrown out points correct. It'll continue to get those thrown out points correct because it's decision boundary consistent. So the in-sample error does not change. What about the out-of-sample errors? Now we've thrown away some data points. What about the out-of-sample error for classifying using this reduced data set? So think about it for a couple of seconds. Okay. Does the out-of-sample error change? Okay, now if you're coming back just for the ride, the answer is no. Because why? Because the actual final hypothesis has not changed. Okay. That's the meaning of decision boundary consistent. We've thrown away data points that do not affect the decision boundary. Okay. So the out-of-sample error also does not change. Now, it turns out that trying to find a minimal set or even a set that's reasonably small that can maintain the same decision boundary is a bit of a challenging problem. But certainly people are interested in working on that problem. Let's define a sort of a more aggressive way of throwing out data. And that's what I'm going to show you next. And the idea here in this more aggressive way of throwing out data, well, A, it can throw out more data, and B, it's a little easier to accomplish in practice. So what's this more aggressive way of throwing out data? Throw out data and throw out as much data as you can with the goal that whatever final hypothesis you have continues to classify all the data points correctly. Okay. So in the case of k equals 1, so because what we want to do is the original classifier. So this original classifier classifies all the data points correctly. So can we throw away a whole bunch of data and continue to classify all the data points correctly? And here, look, I've now managed to throw away more points. Okay, I've thrown away these shaded X's, and I've thrown away 3 shaded X's and 4 shaded blue points. So I've only kept 4 data points, Okay? And the corresponding decision boundary for these 4 data points, well, it's not the same anymore. So my goal was not to keep the decision boundary exactly the same. That was not my goal. Okay? The goal was not to keep the decision boundary exactly the same. So I have gotten a new final hypothesis, G. Okay? My goal was to preserve. So here I have, you can think of this as G full, and here I have the deficient G, G minus. Okay, so G, G minus. Why G minus? Because this is the final hypothesis that's, produced using a deficient data set in some sense, one that's missing some points. Okay, so G, G minus. And the idea is that G minus, the G minus, when evaluated on my data points, okay, is the same value as G evaluated on my data points. So G on the data points is unchanged. Now, compare with the previous situation, G was unchanged. The entire decision boundary was unchanged. That was decision boundary consistent. Okay, there's more aggressive way to throw out data points. I didn't require that the decision boundary must be consistent. All I'm requiring is that your classifications on the training set for the new data must be consistent with your classifications on the training set for the old data. So G on the data is unchanged. Okay, that's a much weaker condition. It's a much easier condition to satisfy. And for example, I've been able to throw away 7 data points now, and look, all the points that were previously in a blue region are still in a blue region, and all the points that were previously in a red region are still in a red region. Okay, so let's ask the same questions. Did E in change? Okay, pause the video, 1, 2, and if you're coming back and you say E in does not change, then you're correct. If you're just coming back for the ride, there you go. E in has not changed, because look, all these red data points classified correctly. They're still classified correctly. All the blue data points are classified correctly as they were before. Okay? So the in-sample error has not changed. What about the out-of-sample error? Now, in general, yes. In general, yes. Why? Because look, the boundary has changed. So the function has changed. The final hypothesis has changed. And if the final hypothesis changes, then you expect its out-of-sample error to change. Okay? So let's compare the two one more time, just to make sure that we understand exactly what's going on. So you have your original data and the original boundary. We can ask, can we throw out as much data as possible, but keep enough data to exactly remember the boundary? Okay. That's decision boundary consistent pruning of the data. Okay. Or we can ask, can we even throw away more data? Okay. Now we might not be able to remember the exact boundary, okay, but we are still able to classify the data correctly with whatever data we kept. Okay. So in some sense, is the goal to keep the whole hypothesis unchanged, or just the hypothesis's predictions for the data set unchanged? Okay, and we say that throwing away data such that you manage to classify all the data consistently with the situation where you kept all the data. Okay, we call that training set consistent. It's a much weaker condition than decision boundary consistent, and because it's a much weaker condition, it's a little bit easier for us to accomplish, and we can be much more aggressive in throwing out data. Okay, so we're going to work with training set consistent. Okay, now I want to emphasize that training set consistent doesn't, if you're working as we are here with k equals 1, then training set consistent means throw away as much data as you can while maintaining E in 0. Okay? And the reason while maintaining E in 0 is because the original full data has E in of 0. But if you're working with k bigger than 1, training set consistent doesn't necessarily mean you have to get E in 0. So here's an example with 3 nearest neighbors. So here's the data set. Okay, so it's the old data set, same data set. Okay, but now I'm doing 3 nearest neighbors. So let's look at this point here. Okay, it's actually going to be, this red point is actually going to be classified blue by this data if you do 3 nearest neighbor. Because for this red point, what are the 3 nearest neighbors? The 3 nearest neighbors are itself and these 2 blue points. Okay, so the majority is blue, so this guy gets blue. In fact, the whole blue region is shown here. Okay, for the 3 nearest neighbor classifier. And you see that some of the points are misclassified. This red point is misclassified, this blue point is misclassified. Okay. So the full data set classifies some points incorrectly. So the full data set is making 2 in-sample errors here. And now when we talk about training set consistent, we're trying to throw away as much data as we can so that we still maintain, for the 3 nearest neighbor rule with the data that we retain, we still maintain the same classifications on the data. That doesn't mean that we have 0 error. It just means that we want to maintain the same classifications on the data. And so here's an example. So we've thrown away a lot of data. Okay, we've thrown away 1, 2, 3, 4, 5, 6, 7. We've thrown away 7 data points. So we've kept just these 4. And we could have even thrown away more, just illustrating here. Okay, and the new classification boundary is this blue region. Okay, and if you look, the blue region classifies all these guys blue, and and this red point also blue. Okay, but that's what it was before. It was classified blue before. Okay, and so that's fine. We are still training set consistent. And this blue data point, which was classified red before, is also classified red now. So the classifications of the training data have not changed. That is what training set consistent means. Okay, so now let's go to the board. I'm going to I'm going to develop for you a very simple algorithm. It's a pretty aggressive algorithm at throwing out data. And what it guarantees is at the end, you will have a training set consistent, set of a subset of the data set that you have retained, and it's usually much smaller than the original data set. And what we can guarantee is that for the retained data, it's going to classify all the in-sample training points the same way it was classified by the full data. Okay? So let's go and see a very simple algorithm that aggressively throws out data and produces a training set consistent hypothesis, and using just a small subset of the data. It's called the condensed nearest neighbor algorithm. Okay. We're gonna discuss the condensed nearest neighbor algorithm. So at a high level, what does it do? It takes your original data set and condenses it to a much smaller data set by throwing out a lot of data. Okay. And now you treat this condensed data as your full data set, and you run your nearest neighbor classifier with respect to that condensed data set. Okay. And hence, condensed nearest neighbor. In fact, we usually abbreviate this to CNN, and it's definitely a newsworthy algorithm. Now, I just want to mention quickly that the condensed data that's produced by this algorithm depends on your choice of k. So if you run it with k equals 3, let's say, okay, and then if you run it with k equals 5, you will generally produce different condensed data sets. They might even have very different sizes. So you need to know what value of k you are using in order to run the condensed nearest neighbor algorithm. Okay, you can't just run the condensed nearest neighbor algorithm, produce a condensed data set, and then decide, okay, I'm going to use k equals 5 with that condensed data. And then maybe I'll use k equals 11 on another day. No, the condensed data is specific to a particular choice of k. Okay, and it'll be a different condensed data if you change your choice of k. Just pointing it out. So I'm going to illustrate with k equals 3. And this data set, nice 2-dimensional data set where we can visualize things. Okay, and in general, you have a data set D, which is, we used to call this Dn. I'm just going to drop the n for the moment. We have a data set D, which is, your data set has x values, x1, x2 inputs, xn, and y values, y1, y2, up to yn. Okay. Now, it's important for me to sort of emphasize and for you guys to sort of appreciate that, the nearest neighbor classifier, even though it doesn't look like it produces a final hypothesis, it seems to produce a way to classify a test point, but it produces a final hypothesis. It's just that final hypothesis is, there's no training involved, and you take a test point and you compare with the closest neighbor or the closest k neighbors. Okay? But at the end of the day, this does produce a final hypothesis G sub d of x. Okay? It's a final hypothesis that can classify any x. Okay? And it depends on the data set in a very direct way, because you have to carry around this data set with you. Okay, and we can use this final hypothesis to classify all the training data points. So you can use any final hypothesis to classify your training data. So you can compute the in-sample classifications, y1 hat, y2 hat, and so on up to yn hat. Okay, where yi hat is equal to g sub d of xi. Okay, so you run your nearest neighbor classifier on your data. Okay, and you get yi hats. And in general, it's not necessarily the case that the classifications of your training data produced by your final hypothesis from the k nearest neighbor, for example, for k equals 3, match the target value. Okay. Now, quick pop quiz. When k equals 1, What's the relationship between the yi hats and the yi's? I'll give you a couple of seconds. 1, 2, 3, 4, 5. Pause the video. Okay, if you paused and you're coming back just for the ride, or you paused and you answered, they're equal when k equals 1. Bingo, you've understood the one nearest neighbor algorithm. Fantastic. Okay, because the one nearest neighbor has in-sample error 0. It's all the training points classified correctly, almost by construction. But when k is bigger than 1, that's not necessarily the case. Now, I forgot to mention maybe, but we typically always choose k to be odd for the obvious reason that we want to take the majority of our k nearest neighbors, and it helps if you have an odd number when you're taking a majority. Okay? Otherwise, you need a tie-breaking mechanism. That's more complicated. All right. Okay. So this is sort of the background. This is what k nearest neighbor is doing. Now, what we're going to do is we're going to try to produce a subset of this data set, much smaller subset than the full data. Okay, and for this subset, we will produce a subset S. Okay, and for this subset, you can compute the k nearest neighbor classifier. So you can compute g sub S of x. Okay, and what we would like is that g sub d of x is of xi is equal to g sub s of xi. Okay. In other words, if you use this subset final hypothesis to classify all the data points, then it will indeed be the case that the subset produces the same yi hats. Okay. That's the goal of a training consistent subset. Okay. So now we're going to start this subset. We're going to create this subset incrementally, and we'll start at the simplest possible subset, empty. So we start with S equals the empty set. Standard notation phi for the empty set. Okay. And now we realize that we're running the 3 nearest neighbor algorithm, and it doesn't make sense to run a 3 nearest neighbor algorithm with fewer than 3 data points. Okay. So the first obvious step is to add at least 3 data points into S. Okay. So which 3 data points to add into S? Just pick 3 randomly. So add 3. Well, add k, in general k, which in this case equals 3 data points, into S. Okay, so, in this example, I've got some blue points and some red points. Let's imagine I pick 3 random data points. Okay, so let's say I pick this guy, put it in a black box. I'll pick this guy, and I'll pick this guy. Okay, so 3 black points. Okay. And at any time when you have we typically call S the working set. At any time when you have a working set, you can compute this the k nearest neighbor hypothesis that's produced by that working set, g sub s of x, g sub s of x. Okay. So quick pop quiz. What is g sub s of x for my working set, which consists of these 3 boxed points, where I'm running the 3 nearest neighbor. So G sub S is the 3 nearest neighbor algorithm, 3 nearest neighbor classifier using S. So pause the video. Okay, I'll give you 1, 2, 3 seconds. Okay, now if you're coming back, or you didn't pause the video and you're here just for the ride, okay, you should have said that, with respect to these 3 points, the 3 nearest neighbor classifier is a very simple classifier. What is it? It classifies the whole space as blue. Now let's see why. Because you only have these 3 points in your data set, so take any point and find the 3 nearest neighbors. Well, there are only 3 points in the data set, so the 3 nearest neighbors are these 3 points. What's the majority among these 3 points? Blue. Okay, so any point has these 3 as the 3 nearest neighbors when you are restricted to S. Okay, and those 3 nearest neighbors, the majority is blue, so any point is classified blue. End of story. Bingo. Okay. So every training point here is classified blue, and I'll highlight one of them, this guy. Okay, I'll make it solid blue. Okay, so solid blue point, blue, is classified blue by S. So I've written it in blue to highlight the fact that this solid blue point is classified in blue. In fact, it's true that every point is classified in blue. So you might wonder, why did I pick this solid blue point? So let me write this in the terminology we have there by S. So G sub S of the solid blue point is equal to +1, or blue. Okay, blue, +1. Okay, because blue is +1. Okay, why I highlighted this guy, and maybe you figured it out by now, is let's see what is G sub D of solid blue point. G sub D of, solid blue point. What is that? Okay. Well, for the whole data set. Now, what are the three nearest neighbors? Remember, that's where k is coming in. So that's why I said that k is important when you're running this algorithm. So what is the three nearest neighbor classification of this point when you're classifying with the whole data set? Well, you have to find the three nearest neighbors. So what are those three nearest neighbors? Well, if you're classifying this point, the nearest neighbor is the point itself. Okay, but then what are the next two nearest neighbors? There's this guy and this guy. Okay, so if you look at the three nearest neighbors of this solid blue point, the majority is red. So this is plus 1. Minus 1. I'm even using red and I wrote plus 1. Minus 1. Okay, what do we observe? We observe that the current working set S and the data set D disagree on this training point, on that point that's in the data set. So this point, let's call it X star. Let's call it X star, reveals a training set inconsistency. A training set inconsistency. Okay. And so we conclude that S is not training set consistent. So we come to the next step in the algorithm. So you've now got a working set S that's non-trivial, non-empty. So there are two cases. Okay. If S is training set consistent, then you're done. You're done. So the other case is S is not training set consistent. And now this is going to remind you a little bit of the PLA. If S is not training set consistent, then there must be some data point X star which reveals the inconsistency. So there must be some, so then there exists a data point X star and its corresponding Y star, which reveals the inconsistency. Okay? It must be there. Okay? And in this case, it's this solid blue point. What is the inconsistency? The inconsistency is that G sub D of X star is not equal to G sub S of X star. That's what it means to be inconsistent. Notice that Y star, the true classification, the target classification of X star is not coming into the definition of inconsistency. I'm just emphasizing this multiple times because that's a common confusion that students have. Okay? You think that inconsistent means that G sub S of X star is not equal to Y star. No, Y star is not in this definition of inconsistency. Inconsistency is comparing G sub D of X star with G sub S of X star. Okay, important. Okay, so what do we do about this? Well, we have to add a point to X star. So, now it's very tempting, and you probably guessed that we're going to add X star into the data set S. Okay, but that's not quite right. Okay, it's not necessarily the case that X star is the right point. It could be the right point, but in this example, for instance, it is not the right point to add. Okay. So I'll just note it here parenthetically. Okay. We're going to add. We need to augment S. We need to add a point to S. Okay. And that point is not necessarily X star. Not necessarily X star. Okay. So I'm just adding that parenthetically. I could have just told you what point to add, but let me first, point out that it's not necessarily X star. Now let me show you why. Okay, so you can think of X star as, it's revealed the inconsistency. So, G sub D of X star is something, plus or minus 1. Okay, in this case, minus 1. And G sub X of S star, G sub S of X star is the opposite. So in this case, plus 1. Okay. So we need to add a point that's going to get G sub X of X star closer to what it should be. We want to improve the situation with respect to X star. Okay. Now, in order to improve the situation with respect to X star, we need to look at the nature of the inconsistency. So what's the nature of the inconsistency? S says that X star is plus 1 and D says that X star is minus 1. So the classification of the point, the true classification of the point we add should be negative. Because we're trying to get this point to be classified as negative. It doesn't make sense to add positive points into your set S. You should add negative points into your set S. And you see here, this point is positive. So if we added X star, it's not going to help the classification of X star. It's going to hurt, actually. It's going to make it more likely the propensity to be classified as +1 will increase. Okay? So in this example, we need to add a red point in. And in general, we need to add a point into S that has the same classification as GD of X star. By same classification, I mean target classification. So we need to add a point into S with the Y value. Now this is the target Y value, not Y hat, the target Y value of GD X star. And which point? Add a point into S. Which point? That's where X star comes in. Add the closest point to X star that's not already in S. The closest such point not in S. Okay, now why closest? Because we're trying to improve the classification on this X star. We're trying to get this guy to be classified as -1. And because the K nearest neighbor algorithm looks at nearby points, we want to add a close point to this guy, which is classified as -1, or more generally as G sub D of X star. And so what better point than the closest? Okay. So in this example, we look around the whole data set for among the -1 points and look for the closest one to this guy, which is this. And so this is the guy we add. Add this to S, at least in this iteration. Okay? And so this tells you how to add a point to S in order to improve the situation for the bad guy, the bad point that's revealing my inconsistency. And that's basically the algorithm. Now we just repeat. So rinse and repeat in some sense. Okay? So repeat, until S is training set consistent. Okay, so you might have some questions. First, how do I know that such a point exists? How do I know that there is a point in the data set that's not in S, which has the classification G sub D of X star? Okay, so I leave this for you to rigorously prove yourself, but here's the basic idea, and it's sort of kind of self-evident. Well, you know, the training set is getting this guy wrong with respect to the full data. So the only way the full data can get this guy as -1 when this is +1 is if there are other data points closer to X star, which are -1, that are not captured in S. So those closer data points to X star that are -1 are not in S. So that proves that such a data point that's not in S, which is classified as G sub D of X star, must exist. Okay. So such a point must exist. So this step is well defined. So now the only other concern is, how do I know that this algorithm will stop? Okay. How do I know that you will ultimately reach a working set S, which is training set consistent? Okay, so now we have to look at the algorithm. What does the algorithm do? At every step, either you're done or you add a point, and we know that you add a point. Okay. Well, so how many times can this step be executed? At most n times. Because after you execute this at most n times, you have added n points. You have added the whole data set. Okay? And the whole data set is certainly consistent with itself. Okay? If S is D, then we're done. Okay? So we know that this algorithm runs for at most n steps. Okay? And so and whenever it stops, okay, which is either at n steps when it contains the whole data set, or it stops of its own accord, i.e. it stops when S is training set consistent. So theorem, and it's not really a theorem, you can prove it yourself. Theorem. It's a really baby theorem compared to some of the other theorems we have seen. Okay. First, the algorithm is well defined. In other words, this point always exists. 1. Algorithm is well defined. 2. It can only run for at most n steps. At most n steps. 3. When it stops, the working set S is guaranteed to be training set consistent. So when it terminates, upon termination, S must be training set consistent. Okay, and so that's the condensed nearest neighbor algorithm, CNN. Very newsworthy. Okay, it's relatively simple. The basic idea is iterative. At every step, if you're not training set consistent, add a point that's going to improve the training set consistency with respect to the one, at least with respect to the point that is revealing the inconsistency. So let me show you, the condensed nearest neighbor algorithm for the digits data. Okay, so I'm showing you the digits data. We've seen this picture several times already. So on the left, we have the one nearest neighbor algorithm, and on the right, we have the 21 nearest neighbor algorithm, so k bigger than 1. Okay, and as you can see, the one nearest neighbor algorithm, more complex decision surface. The 21 nearest neighbor algorithm, more smooth. Okay, so we've seen all these things before. But what we're illustrating now is I'm going to show you what happens when we run the CNN algorithm, the condensed nearest neighbor algorithm, for the one nearest neighbor and for the 21 nearest neighbor. And there, boom. Okay, wow. Look at how much data is thrown away. And then look also at how reasonably well preserved the full decision boundary is. It's not perfectly preserved. That would be decision boundary consistent. Much harder to accomplish, to remember the entire decision boundary. But, what we have produced are much smaller data sets. Okay, and we can get factors. Sometimes you can even get a factor of 100 or more shrinkage in the data set size. Okay, and, what we know for sure is that with respect to the retained data, the classifications on all the data are exactly the same as if you ran the same k nearest neighbor algorithm with all the data and classified the training data. Okay. Now you might wonder, there are still some spurious looking data points. Those have to do with, the randomness in the algorithm. Okay, so we start with a random data set, and then at every we pick a training set point that reveals the training set inconsistency. Well, which one did we pick? So there's a lot of randomness in this algorithm. Okay, and depending on the specific realization of that randomness, you can get very different results. But generally, you get a big shrinkage in the data, no matter what instance of randomness you encounter. Okay, and so that raises the question: is it possible to find efficiently the smallest subset of the data that's training set consistent? And you don't need to restrict yourself to a subset of the data. Is it possible to find the smallest set of points such that if you classify with respect to those points, you will be training set consistent? When those points are not restricted to be data points, sometimes we call them prototypes. And it turns out that problem, finding the minimum training set consistent subset of the data, that's NP hard. So in a very formal sense, it is a computationally hard problem. Okay, but who are we to complain? We're getting such good reduction anyway, so be happy in some sense. Okay, now the fact that it's training set consistent, especially if you use a reasonably large value of k and you have a reasonably large amount of data, means that the in-sample error is preserved. Okay, and we know that if you've chosen the right size of k, then the out-of-sample error is close to optimal, and the out-of-sample error is close to the in-sample error. And if you've preserved the in-sample error, then you've gotten a good out-of-sample error as well. Okay, so we can also make arguments. Okay, I gave you the high-level heuristic argument, but we can also make arguments that getting a training set consistent data set, okay, will preserve your performance. You're not sacrificing out-of-sample performance. You're definitely not sacrificing in-sample performance. Okay. All right, so that addresses the memory issue. So now we can, significantly lower the memory footprint of this algorithm, of the k nearest neighbor algorithm. We don't have to carry around the whole data set. We only need to carry around the condensed data set. What you will also notice is that for the different choices of k, the condensed data sets are quite different. And that has to do with the fact that the algorithm intimately depends on k, because, k is what defines G sub d and G sub s. Okay. So, we've now got a condensed data set that's good, that represents the full data set. So you can imagine the 5-year-old doing something like this. Anytime a new horse comes, it probably says, do I need this new horse? Well, maybe I do. Or, you know what? I'll keep this new horse in my memory and throw that other one in the dark light. That's useless. Okay. So condensing the data is a very powerful tool. Also, in addition to, saving us memory, it can highlight the important, the useful, the critical data. Okay. All right. So that's the memory issue. It also helps with computation, because now computing G sub S is much faster than computing G sub D. Okay. But let us now specifically tackle the computation issue, how to find the nearest neighbor quickly, okay? Assuming that you've already done all your condensing and stuff, and now the data set is fixed. Okay? And so now it's just an algorithmic question and a geometric question of how do you store the data, and then how do you quickly find the nearest neighbor. Okay? And we'll focus on the nearest neighbor, but the same discussion applies to k nearest neighbor. Okay? Okay, so finding the nearest neighbor. So the algorithmic efficiency issue. What I'm going to show you essentially falls into the class of techniques called branch and bound. Okay, so branch and bound. Okay. Now, the idea is that there's a pre-processing step which puts the data into a nice, convenient geometric form. Okay, so let's start by imagining that the data has been put into this nice geometric convenient form, and that presupposes that it can be put. So it's possible to put the data into this form, okay? And we'll address that issue next of how do we put the data into this form, okay? So imagine that the data points, look like this, after I've, put them into this form, and you'll get the picture of what's going on very quickly. Okay, so there's the data points. Some data points are like this, okay, and then some data points are like that, okay. And so when you look at this, you're going to be thinking to yourself, that looks like clustering. Yes, and that's going to play a role here. Okay, so, imagine that we have two sets of data. Let's imagine them to be called clusters for whatever reason. Okay, so let's call this cluster S1, set 1. Okay, so this is set 1. Okay, and this is set 2. Okay, and, associated to every cluster, you have a central point. So let me, put the central point. And we will call this mu1, mu2. Okay, and you can think there's also a radius. So there's a radius, R1, R2. Okay, so, you might say, well, how do we know the data can be put into that form, and how are we going to get it into that form? Well, those are issues we will address later. For the moment, I just want to describe for you the branch and bound technique. Okay, so, this is the data, and the goal is to find the nearest neighbor quickly. Okay, so let's suppose that we have a test point x, okay, and x is going to be closer to one or other of these clusters, of these groups of data points. So let's imagine that x is closer to S1. Okay, so now we're looking for the nearest neighbor to x. So the natural thing to do is to start by looking for the nearest neighbor to x in S1. So you jump into S1. So jump into S1 and find the nearest neighbor to x, and find its nearest neighbor to x. Okay, that's a set of points. Okay, we can certainly, solve the nearest neighbor problem just restricted to S1. So let's say that returns x1, and remember we called it x1 in square brackets, so x square 1. Okay, but now we don't know if that's the true nearest neighbor because it's just the nearest neighbor in S1. There could be a closer point in S2. So let's call that our temporary nearest neighbor, x square 1 hat. Okay, it's our conjecture for the nearest neighbor. Okay, now this jumping into S1 and finding the nearest neighbor in S1. Okay, that's the branch step. So this is called the branch step. That's the branch step. If you can think about it, I have two branches and I'm going down one of the branches. And so that immediately generalizes if the data is, represented not just as two sets, but as a number of sets. Let's say k sets, k clusters. Okay, but I'm just illustrating for two. You'll get the idea. Okay, so now what do we do? Well, the simplest thing to do is now that we've got an x1 hat, go into S2, go into the second set and find the closest. Okay, but then that's, how have we gained? We're going to be comparing, x to every data point. Okay, and so this is where the bound step comes in. So the bound step. Okay, and, the question we ask is there a criterion that we can quickly check, okay, that will tell us whether or not we need to go into the set S2? So is there a quick criterion to bound the closest point so we can check quickly if we need to go into S2. Okay, so that's the goal, that's the idea. Okay. Now, let's think, what's the closest that a point in S2 can be to X? Well, there's the distance to mu. Okay, so the closest, and that's where we get this notion of the bound. The closest point in S2 has distance, has distance, X minus mu is the distance to the center, but then it can come back at most a distance R2. So you can, the closest point is the point that is, if you take X and send a ray to this radius and then come back, to this point where you hit at the surface, that's the closest point. Okay, so the closest point in S2 has distance X minus mu2, okay, minus R2. That's the closest point in S2 to X. I mean, not necessarily the closest point, but that's the closest any point can be if it's in this set which has a radius of R2. Okay, has an upper bound of R2. Okay, so let's think about this. If this bound, if the closest point or the closest distance that any point can be is greater than the distance we found, if this is greater than or equal to even the distance from X to the closest neighbor, x1 hat, x square hat. If this is greater, then we're done. We don't even need to go in there. So this is called the bound condition. This is called the bound condition. Okay. And so look what we have done. We went into S1, we got the closest neighbor x hat square 1, okay, and then we check the bound condition. Okay, if the distance that we have already achieved is less than or equal to the minimum distance to any point in this set, which is given by this bound, which is lower bounded by this bound. So if you've already accomplished this, there's no point going in there. So we save ourselves a huge amount of search. Maybe half the search could be saved. Okay, so if this bound condition holds, if this holds, implies you don't need to search S2. Okay, and so we have saved roughly half the work. Okay, and that's it. That's the branch and bound algorithm. Okay, now let me just mention that this is a very ongoing, cutting edge research issue, which is how to find the closest data point to a given test point quickly, how to store the data efficiently. So we'll study that, shortly. And this is a mechanism that is sort of, in some sense, guaranteed to work. Okay, the failure probability is 0. The only problem is that if the bound condition does not hold, then you may have to search S2 and you haven't gained anything. Okay, so that's the first thing. So first observations. It is guaranteed to produce the nearest neighbor. So produces nearest neighbor. And that's a guarantee. Okay. The second thing we can observe is that, there's nothing to stop this process from occurring recursively. So when we jump into S1 could also be stored as a pair of, or maybe 3 or 4, clusters, subclusters. So we can hierarchically run the branch and bound algorithm, and that's usually how it's done, and that's how you gain the most savings. Okay, because it's not that so you'll gain a factor of 2 here, and then you'll gain a factor of 2 here, and a factor of 2 there, and a factor of 2 each time you go down, and so it results in a potentially logarithmic search time instead of linear search time. So you can do this. You can do this recursively. Okay. Now, what's the sort of bad news? The bad news is, it's guaranteed to produce a nearest neighbor, but the worst case runtime can be order of n. So you may not have gained anything. Worst case runtime can be omega of n. So you may not gain, because you may come out of here, and each time you come out and check the bound condition, it fails. So each time you come out, you have to search the other set, so you don't gain anything. Okay. Now, part of that is because we want an exact algorithm. The algorithm must work. Okay. So some of the areas in which research is done are to say, well, can we relax some of these conditions and get better algorithms? So how do we relax? Maybe we can say, you know what? With high probability, your algorithm's running time is logarithmic. Now, this particular algorithm, if you have good clusters, it turns out that the expected running time is logarithmic. But maybe we can get with high probability logarithmic, or even with high probability constant running time, okay, depending on assumptions about the distribution. Okay, so that's one way in which you can try to improve the algorithms. In other words, the algorithm almost always finishes quickly. Okay, and that's this kind of algorithm. Almost always finishes quickly with the exact answer. The other way in which you can relax these conditions is to say, you know what? I want an algorithm that, always finishes quickly. But what you must guarantee is that it doesn't necessarily produce the nearest neighbor, but if it produces a neighbor, there is no other data point that's, let's say, a factor of 2 closer. Okay? So it produces an approximate nearest neighbor in that sense. Okay? So there's a lot of research in how to relax the requirements of the nearest neighbor algorithm to make it more efficient. But then when you relax those requirements, what happens to the E out, being nearly optimal? So then that's another issue, is, to analyze how the algorithm, if you relax it and don't produce exactly the nearest neighbor, well, then will you still be able to get the near optimal convergence? Okay. So that's, the sort of, basically, in some sense, what's going on with respect to the research in this hard problem. Okay, but now let's get back to our algorithm, which is a relatively simple algorithm, and ask 2 questions. When do we gain? Okay, and by studying when we gain, in other words, when does the branch condition hold, that'll tell us the condition that we need for these, sets, the geometric condition that we need for these sets. Okay, and when we have that geometric condition that we need for these sets, then we can say, how do we set about putting our data into that format? Okay, so when do we gain? We gain when the branch condition holds. Okay, so let's see, when does the branch condition hold? When this is true. Okay, so we gain when this is true, when, x minus x hat 1, let's see, x minus x hat 1, x minus x hat 1 is less equal to, x minus mu 2 minus r2. Okay, that's when we gain. Okay, and I'm going to observe that x minus x hat 1 is at least as large. Okay, x minus x hat 1 is less equal to, x minus x hat 1 is less equal to the distance from x to the center plus r1. So this distance. Okay, so this is less equal to x minus mu 1 plus r1. Okay, so this guy is less than equal to that. And if this guy is less equal to that, then for sure this guy is less equal to that. So the bound condition will hold. A sufficient condition is this condition. So I've simplified because I want to analyze, when does the bound condition hold. Okay, so it suffices that x minus mu 1 plus r1 is less equal to x minus mu 2 minus r2. So let's rearrange. r1 plus r2. R1 plus R2 is less equal to, and we would typically like it to be much less than, okay, so R1 plus R2 is less equal to x minus mu 2 plus, minus x minus mu 1. Okay, so now let's look at what's going on here. Okay, so this is x minus mu 2. Okay, so this is x minus mu 2. x minus mu2. Okay. This distance here is mu2 minus mu1. Okay. And now, the reason, now this is just heuristic because I'm just trying to understand when will the bound condition hold. Okay. So, this guy minus this guy, so this guy minus this guy, okay, so if this guy is small, and that's why we went into S1, so this here is x minus mu1. So if this guy is small, okay, then this distance is approximately that distance. Okay. So this guy here, now this is just heuristic. I'm not claiming any rigorous argument here. I'm just trying to understand when do we expect the bound condition to hold. This guy here is approximately equal to mu1 minus mu2. Okay. If you want to think about it in a sort of slightly more interesting way, you can say that we know that a minus b in magnitude is at least the magnitude of a minus the magnitude of b. Okay, so here we have magnitude minus magnitude. Okay, so if this at least is almost saturated, then you get, let's say, an approximately equal to. So this minus this is approximately equal to this, the norm of this minus that, and the x's cancel, you get mu1 minus mu2. That's sort of geometrically, suggested in this figure. But none of this is rigorous, by the way. This is just to try to understand what's going on. Okay, and so, approximately the bound condition that we want, so when will the bound condition typically hold, is when R1 plus R2 is less than or equal to, or much, much less than, mu1 minus mu2. Okay, so I'll just box this. Okay, this is when the bound condition is expected to hold often, okay, quote unquote often. Okay, and now let's analyze that. So what's R1 plus R2? R1 is sort of the size of cluster 1. R2 is the size of cluster 2. So in some sense, R1 plus R2 measures what we call the within cluster spread. So typically we call this the within cluster spread. Okay. And what is mu1 minus mu2 in magnitude? It's the difference between these two centers. So that's how far apart, okay, the clusters are. So this is sometimes called the between cluster spread. Sometimes we call this the intra-cluster spread, INTRA cluster spread. And sometimes this is called the inter-cluster spread, INTER cluster spread. Intra meaning inside, inter meaning, between, okay, from one to the other. Okay, and this is a very intuitive condition. Okay, what is it saying? That a branch and bound algorithm is likely to give us the biggest benefits, and especially if you incorporate it in recursively, okay, when your data can be stored in sort of sets of this form, such that the sets themselves are very tight. So their internal radii are small, so they're tight clusters that are well separated. Okay? So the distance between the clusters is large. Okay? Okay. And so this tells us that from the perspective of getting big savings in the branch and bound algorithm, you should try to structure your data and store it in these clusters that are tight and well separated. Okay, so now in seeking to sort of get data into the right form, we can try to optimize that criterion, try to find clusters that are far apart, okay, and tight. Okay, and that is called a clustering criterion. And in fact, even though we derived that clustering criterion from the perspective of making a branch and bound algorithm more efficient, that is actually one of the most commonly used criteria in order to find clusters in the data. Okay. So now, let me show you an algorithm that basically finds clusters in a data that is trying to get this branch and bound criterion to hold as much as possible. Okay. And this algorithm is called Lloyd's algorithm. Okay. So let me erase. Okay. I'll just put the criterion here. Okay. Summary. So the summary of this criterion is that we want R1 plus R2 to be much, much less than mu1 minus mu2. Okay, and then I can erase here and show you an algorithm that attempts to do exactly this. And, we are motivated into this algorithm because we want to make branch and bound more efficient, but actually this is a very general criterion that we use when we try to cluster, when we try to organize the data. So good clusters are tight and well separated. Okay, and the algorithm I'm going to show you that attempts to get clusters that satisfy this kind of a condition is called Lloyd's algorithm. It's a very famous algorithm and lots of work done in analyzing it. So it's called Lloyd's algorithm. Okay, and it's a very simple algorithm. So imagine you have a bunch of data. Okay, so what it says is, well, you must pick centers for your clusters. So pick the first center randomly. Okay. Now, since we want centers to be far apart, okay, we want the centers to be far apart, pick the next center as far from this point as possible. So pick a data point that's as far from the point you just picked as possible. Now you have 2 points. Pick the next point as far from those two as possible. So to maximize the minimum distance to those two. And then pick the next point as far as possible. And then the next point, and then the next point. So now we found the centers. Okay. Because why were we picking them as far as possible? Because we want the centers, we wanted the clusters to be well spread as far apart as possible, i.e. we want their centers to be as far apart as possible. Okay. Now, we know the sort of Voronoi regions that correspond to each center, right? We can construct it. It looks something like that. Okay, so you can construct the Voronoi regions corresponding to each center. Okay, and now all the data points that are owned by that center belong to that cluster. All the data points owned by this center belong to this cluster, and so on. Okay, so all the data points owned by this, and so on and so forth. So here, all these points. Okay, now try to do it with 2 colors if possible, but I don't think I will succeed. So here, I'm going to have to use green. Here's another. Okay, and then, whatever, I'm going to use black here. Okay, so there are my 4 clusters. But now, once I've got data points for the clusters, I can update the center to the actual center of the data that correspond to that cluster. So maybe I'll update this center to here, update that center to here, update this center to maybe here, update this center to here, and so on. Okay? So I'll update the centers, and now I can, recompute the Voronoi regions and recompute what data points are associated with each center, and I can repeat if I want, but more importantly, what I'll do next is that then I'll say, okay, now let me figure out what's the radius of each center. So I take the radius to the furthest point in my cluster. Okay, so now I can construct the radii, and so on. That's called Lloyd's algorithm. Okay. So let me show you Lloyd's algorithm in action, and then we'll summarize. Okay, so here's an example of data, and I'm going to show you Lloyd's algorithm in action. So you start by picking one random point, then you pick a point that's as far away as possible, that stayed within the data, and you repeat, pick points as far away as possible in each iteration. Now you construct the Voronoi diagrams corresponding to your centers. Okay. Now you update the centers so that they are the centers of the actual data that belong to their clusters. Okay, and now you can compute radii. Okay, and there we've got a clustering of the data, real data now, into clusters, and we have explicitly attempted to make the within cluster radii small compared to the between cluster radii by choosing clusters that are far apart. Okay. Now this is an example of data that's not easy to cluster because it's just randomly distributed uniformly. And even with data where there are no real clusters, we can still perform the algorithm. We can perform the algorithm on any data set, but in real data, typically, there are well-defined clusters. Biology books and agriculture books and theoretical physics books. They all cluster nice and tightly within their own regions that are well separated. Okay, so that's Lloyd's algorithm. So today, what have we studied? We studied, the efficiency issues of
of the k-nearest neighbor algorithm. And, it's an ongoing area of research, how to find, the best condensed data and also the most efficient algorithms. And then it's another level of complexity to see how, if you change the algorithm that produces perhaps not the nearest neighbor, then how does it change the out-of-sample error? Okay, lots of interesting algorithmic and statistical issues, machine learning issues to study if you're interested in further research. Okay. But where are we going to go next? Okay. So, one of the things that might have been bugging you about the k-nearest neighbor and the nearest neighbor is, you have your training point X, and you pick your k-nearest neighbors, okay, and that's it. You've picked k. And what if there was another point just here? And what if there were a whole bunch of points just outside that radius of k that were all negative, and these happen to be majority positive? So these don't have any impact. Okay, so it seems a little bit limiting to sort of, in a hard way, restrict your attention to just k. One way of viewing that is all the neighbors within my k closest are getting a uniform weight, let's say equal to 1, and everything else gets a weight 0. Okay. So is there an algorithm that can try to use all the data in classifying X? Perhaps weighting them in a way where, closer data points get more weight and further away data points get less weight. Okay. And so indeed, we're going to go in that direction. And that hypothesis said that learning model that we're going to develop, that we're going to derive actually, is called the radial basis function, learning model. And there are many ways to derive it. We are going to take the view of, extending the nearest neighbor so that you can use all the data, but perhaps weighting data so that far away data points get less weight. Radial basis functions, next. For now, checking out.